Okay, next up, we're going to be looking at how we take the Laplace transform of these piecewise functions, these discontinuous functions. So if you think back to when we did the integral definition of the Laplace transform, we actually did some piecewise examples there. And we can always sort of fall back on that. The idea was we have all of these different rules. They apply just for some interval, some window. So we take our big integral from 0 to infinity, and we break it up into a bunch of little integrals where just one rule applies at a time. We do each of those integrals, and this gives us our Laplace transform of the piecewise function. But it's really nice to have a formula, and so that's what we're going to learn about next. There are going to be two important formulas for taking the Laplace transform when we have multiplication by a step function. One of them is going to be super nice for going forwards because it has a nice, easy left-hand side. So this says that the Laplace transform of a step function that turns on at time A, I'm going to just highlight this A. The Laplace transform of this is going to be e to the negative as. So we get an exponential out front times the Laplace transform of this shifted function. We're going to shift f left by A, and then take the Laplace transform of it. Or if we want to go backwards, we're going to use this other formula because it has a nice, simple right-hand side. This says that if we have e to the negative 8, I guess the format that we're often going to write it in is if you have e to the negative as times y, that this is going to be equal to u(a) of t times y of t minus a. All right, so same sort of thing. If we're taking the inverse Laplace transform, where we have an exponential, our answer is going to look a lot like the inverse Laplace transform of capital Y. It's just going to be, in this case, shifted right by A. And it won't turn on until time A. Okay, next up, let's look at some examples.